Okay, welcome back. Last time we ended up with saying the concept of prochiral center. That prochiral center can be of various types, but one type is that if a carbon is there where two ligands are different, like a methyl and a C2H5, and then it is attached to suppose two hydrogens, then this carbon becomes a prochiral center. Again I repeat, because one transformation, that means if I replace one of these hydrogens by another group which is different from these two, then it becomes a chiral center. So, one transformation you can convert it into a chiral center. Now, exchanging this hydrogen leads to one form, exchanging this hydrogen leads to another form. That is why yesterday we have seen that these two hydrogens are called enantiotopic hydrogens. But these two hydrogens, now we have to give some names. We can always say, we cannot just say this is the beta hydrogen, this is the alpha hydrogen, because this alpha beta depends on how you write it. I can always turn it down and suppose this is HA and HB, and HB now looks beta, but if I rotate the molecule, write it in another fashion like C2H5 on this side and CH3 on this side, then HB becomes alpha and HA becomes beta. So, they can constantly change, the way you write it depends on that, but the descriptor should be independent of that. It does not matter how you write it, but if I assign a descriptor for these hydrogens, not the alpha beta, because alpha beta keeps on changing, a descriptor like RS, then I can name or tell which hydrogen I am talking about. Okay. Now, the way to do the assignment of stereochemical descriptors to this hydrogen, suppose in this case two hydrogens, they are enantiotopic, is that what you do, that if you want to know what is the configuration of these hydrogens, or what is the, not configuration, what is the stereochemical descriptor for this hydrogen, then what you do, you assign priority sequence of all the groups, but when it comes to the, because these two should have the same priority because they are the same atoms, but as you are trying to figure out what is this hydrogen, so you give higher priority to this hydrogen over the other hydrogen which you are not considering. So, when I assign priority of the ligands attached to this carbon, this is C2H5, so that will obviously be 1, this will obviously be 2. Now, since I am trying to figure out what is the stereochemical descriptor for this hydrogen, so I assign this as 3 and this as 4. Now, I look at the absolute configuration, what I am getting. So, I am getting, see, I do not have to convert it into Fisher projection or any other thing, this is simple because this hydrogen is alpha. So, I am looking it away from the fourth group. So, whatever I will see, that is the configuration of the system. So, this becomes S. Now, if that be the case, then this hydrogen will be called a pro S hydrogen. For assigning the stereochemical description of the hydrogen, this hydrogen, then what we will do, the priority sequence will change. We have to give higher priority to this hydrogen over the other hydrogen, okay, because we are considering this hydrogen now. So, this remains still 1, that remains 2, only change is this will be 3 because you are now considering this one, and this will become the fourth priority. So, now you see what is the, you have to be now careful because your H4, the fourth group, is now towards you. Okay. So, whatever you see, you have to do, you have to reverse that in order to assign the configuration. So, what we are saying, this is 1, 2, 3. So, it is going in an anti-clockwise, but actually it is clockwise when seen from the back side, that means away from the fourth group. So, this hydrogen, so this configuration is now R. So, if that be the case, then you call this hydrogen as pro R. So, pro R pro S is the descriptor that is given to the ligands attached to a prochiral center. Remember, it is not always hydrogen, it can be any other group. I give you another example. Suppose I want to figure out which one is pro R and which one is pro S in this system. See, this is a fluorine, another fluorine, and this is a methyl, and this is the ethyl. Almost similar compound, but the hydrogens are replaced by fluorine. See, if I want to know what is the which one is the pro R fluorine, which one is the pro S fluorine, what we have to do? We have to again assign priority, but remember the one which we are considering first amongst these enantiotopic groups, that will be given higher priority over the other. So, amongst this methyl, ethyl and fluorine, which one comes first? Fluorine has higher atomic number. So, this fluorine, because I am considering this fluorine first, so this will be 1, that will be 2, this will be 3 and that will be 4. Okay. So, now you have to, now you need some 3-dimensional vision to check whether it is R or S. Now, again I tell you, you can convert it into the Fisher projection and do it, that is one way, or if you are very good in figuring out from the wedge formula, you can do that. So, for the sake of time, I do it, I look it from this side, because I should look from the opposite side of the 4. So, if I look from this side, this is 1. So, first this is 1, then it goes to 2 and then comes back to 3. So, the direction is clockwise. Okay. So, if the direction is clockwise, so 1, then it goes down. So, 1, then it goes down and then comes back to the plane. So, it is clockwise. So, that will be pro R. Okay. In the same way, you can do the configuration of this, the stereochemical descriptor of this other fluorine, and in that case this will be 1. When you consider this fluorine, this will be 1 and that will be 2. And again you have to look from this side, but if you now look from this side, what happens? First you have fluorine down, one group down, then you come up to the top fluorine 2, then you go to the ethyl. So, it is going in an anti-clockwise fashion. So, that will be your pro S. Okay. I think this is clear. So, basically the same groups have to be considered given priority, but the group that you are considering, that should precede over the group you are not considering in terms of priority sequence. So, that is the concept of stereochemical descriptors for ligands attached to the prochiral center. Okay. This is important because there are many reactions, especially the reactions happening in the body, where the enzymes, which are the natural catalysts, so they can pick up one of these hydrogens, the pro R, they can distinguish between these hydrogens, and they will pick up either the pro R hydrogen or the pro S hydrogen while doing the reaction. Suppose it is an oxidation of hydrogen, then they can pick up, they can discriminate between these two hydrogens. And so, enzymes can discriminate between the pro R and the pro S hydrogen, and the way to describe is to use this concept. Okay. So, that takes care of the stereochemical descriptor of stereogenic centers, then the ligands, and then the spaces, and so more or less that takes care of that part. Now, we will go into another concept, which is with molecules which are flexible in nature, molecules which are not rigid, where there is continuous movement. See, all molecules there is continuous vibration, rotation that is going there, little bit, not rotation, sometimes they are restricted, sometimes they are restricted. Like if you lower the temperature, all these vibrations and rotations will be restricted, okay, because you are not supplying the energy to vibrate or to rotate. Okay. Some molecules the rotation is not allowed even at room temperature. There are some molecules, like in case of a double bond compound, you cannot actually rotate the two ends, one carbon, keeping one carbon fixed, you cannot rotate the other carbon, because that will break the pi bond that is there. So, the rotation is not possible. So, that is called restricted rotation. But if you have a single bond, a carbon carbon single bond, then you have 3 ligands on both sides, okay, and these carbon carbons are attached to each other. Then because it is a single bond, so now there is a possibility of rotation between the carbons. Like suppose I have this molecule, this is the carbon carbon bond, these are attached to 3 ligands, and now see there is no problem as such, you can rotate this carbon freely. But how free is this rotation, that will depend on the relationship between these ligands with the relationship between these ligands. What is the geometrical relationship? So, in terms of this relationship is described in terms of what are called dihedral angles. Dihedral angles are basically angles between planes. So, when I talk about dihedral angles, so if I talk about these two white atoms, the dihedral angles between this CH and this CH is actually containing this CC bond. So, basically one plane containing this CC and CH and the other plane containing this CC and CH. So, that is what is the dihedral angle. So, when I rotate, what is changing is the dihedral angle. Suppose this I call the dihedral angle 0, then now as I rotate I keep changing the dihedral angle. The dihedral angle is increasing, it comes to 120 and then this is 180. Remember, I am considering only these two atoms, and then from 180 it goes to 240 and finally it comes to the back and 360, the complete full rotation. Okay. So, it rotates. The question is, while doing this rotation, as I said, the dihedral angle between these substituents, dihedral angles means, again I repeat, that is actually the plane containing these atoms, but for simplicity we just look at these white bonds and we see that CH bond and that CH bond, what is the angle between these two. Okay. That we, for simplicity, we call that as the dihedral angle. Sometimes it is also called torsional angle, angle of torsion. Okay. So, as I rotate it, we see that in one case, as I rotate it, first of all I have infinite number of possible arrangements in space, infinite number, where the dihedral angles varies from 0 to 360 degree. Okay. So, I have infinite number of possible geometries. Now, what are these called? These are called conformations. Okay. So, the conformations are basically in molecules which are allowed free rotation, and so the infinite number of geometric arrangements that you get while rotating a carbon carbon, say a carbon carbon single bond you are rotating. So, that is the conformations. Okay. What about the energy profile, that when you do these rotations, when you get all these conformations, do they have same energy or not, or do they differ in energy? So, what happens, people have actually found, take the most simple, the simplest of all systems, that is the ethane, because remember it actually happens around CC bond rotation. So, we are not talking about methane, cannot have that conformations. Okay. It starts from ethane, where there is a carbon carbon bond, and that bond has to be single bond, double bond you cannot rotate. So, suppose this is the ethane, and you have, as I said, you have infinite number of conformations possible depending on the dihedral angle between the adjacent bonds. But out of these, people have identified two extreme conformations. One, in case it looks like So, we are drawing the Newman projection formula because that is the best way to describe conformational analysis. See, you have in one case you have this, the molecule will look like this, that means there is, suppose that means the dihedral angle here is 0. If I just consider these two, so suppose these are hydrogens, all are hydrogens, actually all are hydrogens in ethane, but we have to fix somehow, we call this as HA and HA. So, we are talking about the dihedral angle between CHA, C1HA and C2HA, the dihedral angle. And so, we identify two extreme ones. One is where all the bonds are eclipsing each other, as I see it, eclipsing each other, and the other one where the bonds are not eclipsing each other, rather these bonds are in between the other bonds. So, earlier this is eclipsing that one, now what happens, this bond has suppose moved here, suppose this is the HA, so this is the HA. So, you have rotated this one and brought it here, and so you have to that means you are rotating the other ones also. So, other ones are also rotated. Okay. So, these are the two extreme conformations that you get. In between there are different types of dihedral angles. Okay. Here the dihedral angle is here is 60 degree in this conformation, here it is 0. Okay. Now, this form is actually called staggered form. Staggered, that is staggered, and this form is what is called the eclipsed form. Obviously, staggered form will be more stable than the eclipsed form. In case of ethane, we start with ethane, the stability difference between the staggered and the eclipsed varies from the substituent to substituent. If it is ethane, then because of this electronic repulsion between the CH and the CH which are eclipsing each other, this is having more energy than the staggered form. How much more? It is about calculated, it has been determined, it is about 3.3 kilocalorie per mole. Okay. So, when we draw an energy versus dihedral angle, suppose we start from this one, this form, okay, this eclipsed form. So, here the dihedral angle is 0 degree, dihedral angle versus energy. So, what will happen to the energy? The eclipsed form has the highest energy. So, you start from here, then as you move the hydrogens, so energy slowly decreases because the repulsion, that repulsion slowly decreases. So, now ultimately it attains a minimum, but then after, if you further move it, then this HA is now slowly becoming closer to this CH bond. So, the energy starts increasing again. So, what will happen? This will take up like this. So, this is after 60 degree rotation, this is after 120. 120 means you again get these two hydrogens eclipsing each other, then you have a 180 degree rotation, then you have 240 rotation, then you have a 300 degree, and finally a 360, you come back to the eclipsed form. Okay. So, this is the energy profile diagram of ethane, or we call the conformational analysis. Conformational analysis, which means that which means several things, means how the reactivity depends on the conformation, how the energy varies with the conformation. So, this is the variation of energy with dihedral angle. By the way, this is also called torsional angle. Okay. Now, this, so you see there is a maxima, so it alternates between a maxima and the minima. These maxima points are the eclipsed form, the minima points are the staggered forms. Okay. Every point in this diagram, represents a conformation with a particular dihedral angle. Okay. However, the molecule will prefer to exist in this form because that has a minima. First of all, that has got lower energy than the eclipsed form, and the difference in energy is, as I said, is about 3.3 kilocalorie per mole, and 3.3 kilocalorie per mole. Okay. So, more than 99% of the molecule will exist in the staggered form, but that does not prohibit the molecule from undergoing free rotation. See, one staggered form going to the another staggered form, going to another staggered form, and as you raise the temperature, that movement will be more rapid, that interconversion will be more rapid. But here we also introduce, again I repeat, every point in this graph represents a conformation. However, the conformations which lie in the energy minima, in the energy minima, or the minima in the energy profile diagram, that is called conformer. So, we have a special conformer. So, conformers are the ones which lie in the energy minima, and but the conformations are all, every point in this diagram represents a conformation. Okay. But the conformers are the one which lie in the minima. So, eclipsed form is not a conformer because it lies in the maximum, nor the ones which lies in these dots here, they are not conformer. The conformer is only the ones which are lying in the energy minima at this point. So, you must understand the difference between conformations and conformer. So, now come back to we have just introduced this concept. Conformations are the infinite number of arrangements, spatial arrangements that you get while you by rotation around a single bond, not for a diatomic molecule. Remember, if it is only a diatomic molecule, that means suppose it is chlorine, this is chlorine. So, if you rotate, nothing happens unless these are attached to ligands, that means it has to be more than monovalent, okay, these atoms. But let us concentrate on carbon. Carbon has 3 extra groups apart from this carbon-carbon bond. So, by rotation around this carbon-carbon bond, you get infinite number of arrangements in space. So, these infinite number of arrangements are called conformations. Now, these conformations will lie when energy, they have not the same energy. As you rotate, the energy keeps on changing, and the conformations which lie in the minimum in the energy profile diagram, they are called the conformer. Why they are called conformer? Because this is the one which is mostly present in the system. Although it rotates, but at a certain point of time, if you want to see by spectroscopic means which one is present most, then you will find that this is present more than 99%. Okay. So, that is so all conformations are not conformers, but all conformers are also conformations. Okay. So, this fact will become more clear when we go to the higher system like N-butane. I think that will be covered in the next lecture. Okay. Thank you.